we know what neural networks are. If the neural network has a lot of hidden layers, intermediate layers, in different literature sources you can find different numbers, but in general it's like more than 3, then you can name this network deep network. From that, we also have a deep learning. It's like a field how you can build and train a very highly complex models, and especially what are the tricks you can apply to train it reliably. We already know that the process is highly dimensional, very complex, and highly nonlinear. Those should be our models as well. Another point that is like new and why we are talking about deep learning right now is that due to digitalization in the process industries and also in other fields, you have access to a lot of data. So you basically have big data. So you can, for example, use your cell phones to take pictures. There are some metrics, telemetrics that are being collected all the time, and the same in the plants. You can install a lot of sensors. They're not that expensive anymore, and integration of sensors also not that expensive. And in this case, you can actually aggregate, collect such huge amount of data that you can build very real, good, very complex models. The problem is, if you would like to apply the traditional machine learning algorithms, let's say we have the amount of data in our data sets and we have the overall performance. If we're talking about traditional models, for example, linear regression or for classification support vector machines, decision trees, the problem is with those models are, at some points, if you have a lot of data, you do not increase the performance. It might be also challenging to train the model if you have a lot of data, but anyway, the performance will stay approximately the same after a certain value of the data. Let's say we have low amount of data, we have higher amount of data. We have low amount of data. Traditional machine learning methods are just good, and we would apply them because they're easy to train, they're easy to implement, to understand, and so on and so forth. But the problem is we cannot increase the performance even if we have more data. If we go to neural networks, in the field of low amount of data in this range, performance will be approximately the same, maybe even a little bit lower, a little bit higher. But then we have more data, we can get more performance. So let's call it shallow neural network. But at some point, in general, we get high performance, but at some point, the amount of data does not bring us anything anymore. And that's why we are talking about deep learning. So we build more complex models, let's say it's model complexity, and in terms of neural networks, that means the number of layers, number of neurons per layer. If we increase the model complexity and we go in field of deep learning, we will get a better performance from our data. So we can actually have benefits from the big data. And that's exactly why deep learning nowadays is very popular. We have a lot of data and we need the models that can cope with that amount of data and also be effective with those data. Third are the opportunities big data and deep learning have for us, but we also have some challenges for sure. And as I already mentioned last time, most of them are connected to the fact that the larger the model is, the deeper the model is, the more difficult it's to train the model. So the first class of challenges is model training. Why is it the case? Basically, if you have a lot of layers, connected, at some point, the features you have, like you go from this to the right, and then you apply some transformation, further, and to train the model, you basically need to find the gradients. So the gradients, how your output features are dependent from your input features. From your weights, of the parameters. And the deeper your network is, the more layers you have, and you need to combine them, the gradients, and at some point you can face a so-called vanishing gradient problem. So where basically you do not have more gradient change, you do not have any gradient change anymore, and you cannot train your model further. So you start to train your model, the performance increase, and after that nothing happens, just because the input features does not change anything at the end. For that, there are some training techniques were developed, especially for that are very good for deep learning or deep networks, so-called stochastic gradient descent, also Adam, and so on and so forth. There are also additional techniques you need to apply on your network to get them trained properly. But mostly they are small tricks, so you basically apply the same techniques to train your model as shallow neural networks, but you need to apply those additional tricks. Go back to our problem. One of the solutions would be to use so-called residual network or residual connections, where you basically, in addition to your conventional ways to connect your layers, you can also get the input of one of the first layers and then connect it directly to something at the end. And then you have your residual connection, and then it will help with your vanishing gradients. So model training, we have new techniques, and we have also some trick called residual. Another problem with all deep learning networks, they are almost every time overfitted, like by default. What does it mean? You have millions of parameters, of free parameters, and you have the data. That means you can find the set of parameters that will describe your training data perfectly, but then fail on your test data. And to make it more reliable, the training process itself, or to overcome the overfitting, some regularization techniques were developed. You also can apply a regularization technique on traditional machine learning methods, even on linear regression, and similarly you can apply on your neural networks. One of them, the simplest one, is the L2 regularization. The idea behind it So basically you have your weights, but you do want them to be as low as possible. Because in this case, the model during the training tried to find such weights for your network, some sort of a compromise between performance and the lowest weights. It's important because otherwise the model can decide I would like to increase only some of them and the rest would not play any role in my network. But it's not something what we want, and that's why we say let the model distribute the effects of your inputs and intermediate steps in a very even manner. And that's why we apply L2 regularization. We basically try to add additional term to our target function that will use the L2 norm of our weights. Another technique of regularization, it's data augmentation or data set augmentation. The idea behind this that we create additional data instances, or we apply randomly apply transformations on our data in a way that we basically have the same distribution as our original data, but we have additional points. So you can imagine you have for example 9 data points in your data set for one feature, but we would like to have more data to make them to have more variety in your data. In this case, you just say I add additional data points that will follow this absolutely the same distribution as my original data, but I have at the end I will have just more data points. And surprisingly, it does have a positive effect of model performance. Mostly about data augmentation you can read when you, if you're talking about computer vision, deep learning for computer vision problems where you can, for example, rotate an image or flip the image and so on and so forth. And thus you multiply the number of instances, although you do not collect additional data. And similar you can also do for time series. For example, apply noise or do some transformation that does not break your dataset. Another technique of regularization is so-called early stopping. During the training, based on the gradient descent, it's an iterative process. And in this training, the loss function or the value of the loss function normally decreases over the time. At some point when the models start to overfit, it will go up. And it's exactly the point when you need to say I need to stop the training process and take exactly the model when I have the minimal value of the my loss function. And that's why it's called early stopping. You go a little bit further and then you go back. So basically you do not wait until the end of the training process. Another interesting technique of regularization is so-called dropout. You have your neural network, but you want to explicitly force your training process, your model, not to learn a very specific connections, to increase very specific weights, but to make it more robust against some disturbances. And in this case, you say, you predefine a certain probability that your weight will be just dropped out from the calculations. That means you literally, during the training process, if you say, 50%, then you go from layer to layer and randomly select every training iteration 50% of neurons that will be excluded from the calculation. That means that the weights will be 0, and that means they won't learn anything. And exactly in this case, the model is first to learn the other neurons, like this connection, instead of the connections that were switched off by dropout. Also, surprisingly, that have very good results, like performance-wise, and that's why you would like also to apply this technique. Another technique is called batch normalization. Where basically each time you fit a batch to train the model, you normalize it. So for example, if you have one time you have such data, and next time, like the next, you have such data, you just basically say, I will normalize it. It will be from -1 to 1 approximately. And that's all. And what you do, so basically you do not learn the absolute values, but you learn the differences, you learn the patterns in your data. And this helps you to also to overcome overfitting effects. There are for sure more regularization techniques, but those we consider right now are the most popular, and I encourage you to apply them almost every time you train a deep learning network. Yeah, now we know how the model looks like, we know what regularization technique we would like to apply, the challenges, how to answer them. And now let's talk about frameworks. So basically, the model itself, it might be difficult to implement, especially if we are talking about custom structure, regularization technique, especially also model training routine. It's very hard to implement. So you can spend a lot of months, and even in this case, you cannot be sure that your implementation is validated, it works well. And that's why mostly you just use already available frameworks for machine learning. Especially for deep learning, there are, I would say, 2 of them that are popular. Those are so-called PyTorch and TensorFlow. They exist also for different programming languages, but the idea behind them, so basically can create a model of any structure and use not only feed-forwards or create not only feed-forward artificial neural networks, but also, for example, recurrent neural networks, convolutional, because you have the types of neurons already predefined in these packages, and you can just use them. The same as for regularization. You can write, for example, you use the optimizer, Adam optimizer, or stochastic gradient descent, and you do not have to implement them by yourself. For sure, MATLAB is also in the list, has very good toolboxes. The main advantage of MATLAB is though that you can build your model and you can train the model and see and analyze results in an interactive manner. That means you can, for example, instead of programming or code your model, you can just use the graphical user interface, just find the corresponding blocks, put them together, and then as soon as the training is done, you can analyze the results. So there are some handy plots you can use for that, and they are generated automatically in MATLAB. So we have frameworks, we have data we talked about, how we need to preprocess them, we have some regularization, and that's it for deep learning for today.